Good afternoon to everyone. I am Alessandro Greco, a researcher at University of Campania Luigi Vanvitelli, and this ongoing research deals with the investigation of tensile properties of additive manufacturing PEEK at varying of some printing process parameters and considering also some post-processing treatments. So PEEK, as you know, is a high-performance thermoplastic polymer with very good properties. Indeed, it is widely adopted in diverse industries such as aerospace, medical, automotive, and so on. So the characteristics of PEEK are high mechanical strength, high temperature and chemical resistance, is a biocompatible and recyclable material. It allows the possibility for lightweighting structures, and it can be also used in metal replacement application. There are two main production technologies for realizing PEEK parts. One is the injection molding, and the other one is the fused filament fabrication. So the first one is let's say, the most robust and effective one, since it is used for large-scale production. It ensures high performance of the material. However, it suffers some design limitation due to geometrical constraints. So in the table here, we can see some tensile properties of molded PEEK that we can use later as a reference value for comparing our results. On the other hand, we have fused filament fabrication as additive manufacturing technology. It allows a fast and customized production. It allows and gives the possibility to create any complex shape, thanks to the concept of complexity for free that often we associate to additive manufacturing. However, PEEK is a very expensive material, but is also very hard to print. And their mechanical performance strongly depend on printing process setup. So we still need knowledge. In the literature, just by performing a very rapid research on Scopus database, we found that several papers investigated the effect of printing parameters on the tensile properties of additive manufacturing PEEK. However, we have a very high amount of parameters that we can set, so increasing the knowledge of mechanical performance could be also a valid and open issue. Then another interesting aspect is the possibility to perform some post-treatments on PEEK additive manufacturing parts, and studying also which is its effect on the mechanical performance. Finally, a very wide literature gap we found on the literature concerning the fatigue of additive manufacturing PEEK. So just to summarize, we can say that literature still needs knowledge about the influence of the main process parameters on the mechanical performance of additive manufacturing parts, and PEEK in this case. From the literature review, 3 parameters result to be very influent on mechanical properties of polymers in general, and they are infill pattern, layer thickness, and processing temperatures. So we found also that post-processing annealing, in this case, of VM part could improve their mechanical behavior. And about fatigue, we can say that preliminary tensile tests are necessary for designing a proper future campaign. So the aim of this paper, of this research, is to carry out an experimental investigation on tensile behavior of additive manufacturing PEEK by varying the layer thickness and the infill patterns, and considering also eventual post-processing annealing, specifically annealing. So a series of specimens are built or will be built according to, with the geometry according to ASTM D368, and they will be produced by Minifactory Ultra, that is an industrial 3D printer that we have at disposal in our laboratory. Specimen will be built and are built, some of them, by considering 2 levels of layer thickness, 0.15 and 0.25 millimeters, 2 infill patterns, the triangular that is one of the most used by people in general, and rectilinear at minus and plus 45 degree. And then we will also consider an annealing post-process. In the other table, we can see other fixed parameters that are taken by the literature and by the provider of the filament. So we set the best value for them. All the specimen will be tested by an electromechanical testing machine equipped with a 30 kilonewton load cell with a 25 millimeter gauge length and with a cross-head speed set to 1.5 millimeter per minute. A full factorial DOE has been, a design of experiment has been considered to set each combination. In total, we will have 8 combinations, and we will consider 3 repetitions for each combination for a total of 24 specimens that will be subjected to tensile tests. As you can see from the picture, some of part of the specimen have already been produced and tested, and in particular, in the picture, we can say below one of the specimens subjected to annealing, and we can just know how the color is different, and even if not really appreciable, also the geometry of the specimen changed during the annealing. Let's show some preliminary results. So, first of all, from the stress strain curves, we can see that there is a high repeatability of the process. And going more into detail, we can observe that specimen with triangular pattern show more brittle, let's say, behavior, presenting also a net fracture just after the maximum load. Then specimen, on the other hand, specimen with rectilinear patterns show a more ductile behavior, and in general, rectilinear pattern performs better. And this is confirmed by analyzing the results for Young modulus, and for rectilinear pattern specimen, we can reach value comparable with the molded PEEK reference value, that is 3.6 gigapascal. Similarly, we can say that ultimate tensile stress achieved by rectilinear pattern specimen is just 10% lower than the molded PEEK reference value, that is 100 megapascal. And similarly, about the elongation of fracture, rectilinear pattern performs better, even if the average value is still significantly lower than the molded PEEK reference value, that is around 35%. As I anticipated, we will consider also some post-processing, in this case annealing, and just as example, since annealing is a very high time consuming process, I show in this slide some results achieved for one of the series 3 specimen, characterized by 0.25 millimeter layer thickness and triangular infill. On the left, we can see the temperature curve, where we have a 1 hour preheat at 140 Celsius degree. Then there is a ramp up with a speed of 10 Celsius degree per hour. Then a 4 hour long annealing at 220 Celsius degree, and then a cool down with a speed of 10 Celsius degree per hour. Observing the curves on the right, we can observe that in general, annealed specimen perform worse with respect to the non-annealed ones. And this is confirmed by analyzing the Young modulus and the ultimate tensile stress, which decreases about 7% and 13% respectively. And this result was unexpected because it's inconsistent with respect to the literature, where in general, after annealing, polymers should increase the UTS about 10%. But of course, it's just the beginning of this experimental campaign, so we will understand much more in the next week. some consideration about this preliminary result, we can say that infill patterns significantly influence tensile behavior of peak, much than the layer thickness. In particular, rectilinear pattern performs better than the triangular one. And with this pattern, we are able to reach young modulus and UTS values very close to the reference value given by molded peak. Comparing with the existing literature, these results are very consistent by comparing with other papers and research with a similar setup. And as I said before about the annealing, there is an unexpected behavior that we will investigate better in the next future. To conclude, so with the rectilinear pattern, again, we can reach values of young modulus and in general mechanical performance very close to those one provided by molded peak. The annealing, of course, needs to be further investigated. And in the future, we will consider in this campaign also other infill patterns. And we will also perform some geometrical inspection to investigate distortion and to understand how varying printing parameters also the final geometry of the part is influenced. At the end of the campaign, we will have some idea clearer for designing a proper experimental campaign to study the fatigue behavior of this interesting material. Thank you for your attention.
Thank you for the presentation. I ask to the audience if there is any questions. No. I have a curiosity. I don't understand very well what do you mean for triangular infill pattern. So can you explain again, please?
Yes, I can show here. So the specimen inside, in general, the manufacturing inside are characterized by a volume called infill. And about this infill, we can change the pattern inside. So triangular, rectilinear are just two ways of filling this volume inside the specimen. So you can see in the picture, triangular are a series of triangles in the column, while rectilinear just the filament is positioned parallelly, as you can see here, for example, on the surface. And for each layer, in this case, the degree changes. For one layer is 45 degrees, for the other one is minus 45. Similarly to what happened with the composite, let's say. I don't know if it's clear.
Okay, thank you very much. I have another question. Do you plan also to investigate the fatigue behavior, but also the static behavior of the infill pattern 0, 90 degree?
Of course. And I expect that maybe with 0 degrees, so the filament parallel to the tensile direction, maybe we can reach better performance with respect to this one. But of course, we will include this aspect and also some other patterns that can be comparable to rectilinear, but just by studying the literature.